everyone arrive. So just to remind you, you are being recorded now, or the meeting is being recorded, not necessarily you, but anything you say will be recorded. And then, of course, your chat sessions remain as well. Is that true, Jacob? And what evidence do you have to back that up? Okay, let's go ahead and get started. So we have Jacob actually ready to present. So glad that Jacob was able to make it, because I believe Jacob was up next and then Josh. Is that correct?
Yep.
So let's go ahead and Jacob, if you could bring up a presentation and share it, we can start on your devotion and your presentation. Oh, allow. So you should have that little screen thing with the up arrow for sharing.
Hello.
Yes.
All right. Well, so I'm in charge of bringing a devotional and also doing my presentation for today. So I figured I would do something that's pretty relevant to our current situation. So I pulled up James 1, 2 through 4. And it says, "Count it all joy, my brothers, when you meet trials of various kinds, for you know that the testing of your faith produces steadfastness. And let steadfastness have its full effect, that you may be perfect and complete, lacking in nothing." And this was at a time when there was a lot of difficulties going on in the early church, and James is writing to this collection of churches to effectively say, guys, you're going to go through trials, and as long as you hold steadfast, everything will be okay. You're going to struggle, but you'll get through it by the grace of God. And I think it's very relevant with what's been going on with this virus going around, and of course, it's very relevant to myself because I've effectively lost the chance to graduate like I was expecting. So, you know, it's definitely been a struggle, but we will all be okay. We will all get through this. So, all right. So
if the graduation is rescheduled for a later date, do you think you'd come back to Longview
for the graduation? I hope to, certainly.
Good.
But I don't know exactly.
Yeah, none of us know.
If I might be working a full-time job at that point, and if I'm busy with work, then I won't be able to make it to commencement and all that sort of stuff. But okay, let me really quickly swap over to the presentation. Go ahead and start this. Okay, and y'all can see this, right?
Yes.
All right. So I am conducting a presentation on the live demo and the ethical hacking side of Kali. Obviously, you had the first section of the presentation from Och here last Friday. But yeah. So Kali is well known for being one of the best, I shouldn't say exactly the best, Linux suite for ethical or unethical hacking. And it can essentially be compared to pen testing on door locks. Effectively, companies will call various locksmiths in to try and pick locks on their doors. And if these locksmiths are able to very easily pick these doors, then they're able to upgrade their security a little bit and add better locks to it. So typically hacking is defined as getting a system to do something that it wasn't intended to do. So in this situation, hacking is compared to pen testing because you will have a lot of ethical hackers, cybersecurity specialists that will come in, and they will test your systems to make sure that there's no way that they can get in through some sort of backdoor or security flaw that you have in place that you don't know about. And as it is definitely considerably easy to cause serious damage to a system, I'm going to say that the author of this presentation does not condone or promote any illegal activity due to the installation of this Linux package. I'm just going to put that out there for my own sake. To give some idea, Kali itself is not illegal. However, the tools that it allows access to can definitely be used in malicious ways. Kali can be used in many ways for hacking, such as network and Wi-Fi hacking, which, as I've been able to experience myself, is actually really, 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 really easy to do. It's abhorrently shocking how brainless it takes to actually do something like that. With the use of Nmap, you can very easily scan and examine networks, potentially giving you access to any unsecure information on those networks. And on the ethical side, Maltego is actually used for digital forensics to examine and diffuse dangerous or incriminating devices in court trials. I had the chance to try some of that out in a class that Dr. Gowing taught for a couple semesters, and I got the chance to effectively be part of a mock trial where I went in and I searched for information on dummy devices as a way to incriminate a criminal. So that was a lot of fun and really interesting. So when you're doing ethical hacking, which is this cybersecurity side of hacking, you need to take into account your attack strategy, find any open ports to use for your attack, and locate any flaws in the SSL certifications. And this is effectively basically the ground zero. This is where you want to say, okay, I need to hack into this network. I need to see if there's any underlying conditions that might make it a little easier for me to get into this network. So after you've done that, you need to pick your tool. And I provided a couple here. Nmap, as I said again, can be used for locating open ports on a network. It can also be used for bypassing firewalls. GoBuster can be used for finding open directories. Firewalk and Routersploit can be used to abuse or otherwise gain access to a router. I actually did some work with Routersploit in networks. Ghostfisher is used for account manipulation. You often see people who get their bank account information leaked. Typically, the hacker is using some sort of phishing software or algorithm to do that. And of course, Wireshark, if any of you have taken a Dr. Gowing class, you know what Wireshark is. And I was going to show you all how to crack a Wi-Fi point, but I originally put this presentation together back when we were on campus. So I didn't think that IT was necessarily going to be happy with me breaking into the LetNet network. So instead, I'm just going to show y'all a person who already has done this. Just 1 second. I'm bouncing around between various sites and things like that. Oh, no, that is not what we want. Where is it? There we go. All right. So I'm just going to play this quick clip real quick. And this is with a software called Fern. And he's going to go ahead and start an active search for different networks. I'm going to skip forward. He's going to go ahead and pull up that network. And this is a secure network that he hasn't touched before. He's going to go ahead and load a MAC address. And at that point, he has successfully cracked this access point and also deauthenticated the MAC address associated with that, which gives him effectively complete power to choose whichever password he would like to have for that access point, and effectively giving him the ability to hold that network hostage for the time being. And this is actually kind of a common thing that you'll see with loosely secured networks, is people will break in, take control, and then they will ask for money or some other payment in order to get this back. So that is definitely a serious danger to different systems and networks, which is why a cybersecurity major is a really important thing to have right now, because you're going to get a lot more people looking to get their network secured and make sure that they're not easily hackable. So, in conclusion, the strength of Kali is the tools that you can use with it, and what with the recurring prevalence of data leaks and brute force attacks, it is always good to know what is out there. There was a rather large brute force attack on the PlayStation Live network, which exposed a lot of accounts to the public, and that became a serious issue with their security. And so they have since fixed that issue, but it became such a horrendous accident that, it was all over the news during that time. So, all right. Are there any questions? Cool. Well, all right.
So I guess I'll go ahead and take back control here. Yes, a lot of those tools have legitimate uses, but they can also be used for evil. And so, for instance, Wireshark is commonly used when you're testing network traffic and things like that. But yes, it can be used for malicious purposes. Generally, in the defensive side, we look at software that tracks whether port scans are happening and whether the ports are being addressed. And certainly when I worked for a computer security organization, we were using all kinds of data analysis tools to observe traffic to try to detect when people are trying to do are doing malicious patterns or trying to discover new patterns of malicious activity. So we got a lot of clapping hands. Good job. Okay. So we have Josh finishing up the Kali Linux presentations, and then Jessica on the Haiku OS. Let's see, I'm trying to see. And then Ian is up after Jessica. Ian, and then the history of Unix team will be after that. So administratively, we're going to look at Chapter 7, Deadlocks, and Chapter 8, Main Memory are the next two chapters coming up. The Chapter 7 and Deadlocks, because of our move to online and all the things that are going on, is going to be greatly shortened, and unless we have time to go back to it, there probably will not be a quiz on Chapter 7. If you wish to take a quiz on Chapter 7, just let me know, and I'll open it up for you and let you take it. But there will not be, most likely, unless we have more time at the end of the semester, a quiz on Chapter 7. And then we'll go into main memory in Chapter 8. And there's actually two chapters, 8 and 9, that involves the management of memory, because memory management is such an important thing, task that an operating system does. There's actually two chapters worth of information, and we'll go through that and hopefully give you a good feeling of how it is to manage memory, because that is an important concept to understand as you're writing applications, especially regarding performance, how your program performs. Okay. Now let's move on to Chapter 7. So you should see the title slide for Chapter 7, Deadlocks, up. So we are going to go through this quickly, and so it won't be necessary to understand it in great detail, because it actually will not be covered in great detail. I'm just going to skim through Chapter 7, pointing out key points regarding it, but not going into detail, a detailed description. Feel free to still ask questions if something catches your curiosity, or you want to understand something a little bit deeper. So the objectives of this chapter was to develop a description of deadlocks which prevent sets of concurrent processes from completing their task. Basically, two or more processes in terms of process synchronization get stuck, and they're no longer able to proceed. And that would basically can shut down your system if someone's hanging onto the CPU and not releasing it because of a deadlock situation. Then we will discuss a number of different methods for preventing or avoiding deadlocks in a computer system, and we also will discuss how it actually is done in the real world. So first of all, there's a system model of modeling deadlock situations and what conditions result in a deadlock. We won't go through them in great detail, but this is just to let you know that there is a lot of research and a lot of techniques for detecting and trying to prevent the situations that lead to deadlock. So first thing is that there are 4 main situations or criteria that have to be fulfilled in order for a deadlock to happen. The 4 conditions that need to hold for deadlock to happen is mutual exclusion is involved. So we have one process at a time can use a resource. So there's a shared resource that they're competing over with mutual exclusion. Hold and wait. A process is holding at least one resource and is waiting for an additional resource. So they both have to hold a resource and then be waiting for a resource at the same time. The other is it's non-preemptive. Again, this is the decision to go be non-preemptive is a situation of performance maximum usage of your CPU and increasing your performance. In the the other thing that can happen that needs to be in place is circular weight, and that is where there's a circular dependency on the processes that are dealing with the the synchronization for a resource, the process synchronization that we looked at in the previous chapter. So the common technique is a way of graphing it. And here's an example graph of the different processes and the resources. And they go through a graph analysis that will help you determine if a deadlock situation can occur. This is just going through an example, looking for cycles or non-cycles of dependencies to determine if deadlocks are possible. So given that there are techniques to detect it, there are different techniques for handling techniques. I mean, for handling deadlock. So that is ensuring the system will never enter a deadlock state by doing deadlock prevention or avoidance. I have mentioned that one way this is commonly done is to have all the resources that are used by these processes and outlining that the resources can only be accessed in a particular order in order to prevent deadlock. But this does not have a general solution. If any process breaks the rules and doesn't access the resources in the prescribed order, then deadlock can still happen. The other technique is to actually allow the system to enter a deadlock state and detect it when it occurs and then recover. And then recovering is generally killing one of the processes that are involved in the deadlock situation. And then lastly is to ignore the problem, pretend the deadlocks never occurred in the system, and then just deal with the consequences of the deadlock. Of these three, which of these solutions do you think is the most prevalent? Any votes? Okay. So Scott is saying recover. So that is allow the enter the deadlock state to happen and recover. And Bailey says ignore it. And then we have another vote for ignore it. And then Timothy says that we try to have it so that we prevent deadlock. The correct answer is choice number 3. We basically punt and we ignore the problem and pretend that deadlocks never occur. And the reason why this is the most prevalent technique is that the preventative measures involved, other than the simple one of making sure that resources are only accessed in a prescribed order, which can be enforced, but it generally isn't, is because that the performance would suffer too greatly. And so the answer is, since it happens infrequently, that is the way that the solution that has been chose by most operating system is ignore the problem and pretend that deadlocks won't occur because of the performance penalty of the solution. So it's a case where the solutions have been deemed worse than the actual problem, and so we ignore it. And that's why I decided to go through this chapters pretty quickly, because it is strictly an academic exercise at this point, unless one of you brilliant students come up with a great solution to solve this in a economic way that doesn't affect performance too greatly. In general, we punt. And so that's why in your operating system, you can have a situation where the system will just hang. And that is most very commonly a fact is that you had a deadlock situation that wasn't prevented or handled, and the system will just hang. So it's unfortunate, but it is just an academic exercise at this point. There has not been a general purpose technique that has been devised that doesn't have a severe performance penalty to it. So in this decision to ignore the problem, typically the situation of deadlock has been characterized, or it's hoped that it would be very infrequent, say maybe once or twice a year that you will see this. But it'll be interesting to see what happens when we go to more and more multi-core processing and the like, and programs that are trying to take advantage of that. So having more and more multi-threaded and multi-processor systems running, and the even higher cost that it takes to handle deadlock in that situation, whether we will see an upshoot in the number of deadlock situations. So it is a very telling thing that most operating systems have decided to punt on the issue. So just covering the various options that we looked at. Deadlock preventions is restrain the way requests can be made. Like I said, one way is to say process can only access resources in a prescribed order. But again, most systems won't enforce that, and that's because it's probably hard to characterize all the resources that will be used in a particular system, and that it would change. And so generally that's not done. Deadlock avoidance. Here we have 3 different ways that deadlock avoidance could possibly be done. One is a model that requires each process to declare the maximum number of resources of each type that it may need. The second option is deadlock avoidance algorithm, dynamically examines the resource allocation state and make sure that there's no circular wait conditions. Again, that would have to be done statically because the performance hit would be extreme to do that during runtime. And then resource allocation state is defined by the number available and allocated resources and the maximum demands on the processing. So there's these general rules, but the difficulty is enforcing the rules. And then there are various conditions that can be defined that declares when you are in a safe state where deadlock can occur. And so there's been analysis on determining the characteristics of safe states. And then if a system is in a safe state, no deadlocks occur, you know, as you would expect with a safe state. And then in an unsafe state, there is a possibility of deadlock. There's not a guarantee of deadlock in an unsafe state, but it allows for the possibility of a deadlock. And this can be used to help in the efforts to do avoidance. So deadlock detection, which was Scott's guess, we allow this system to enter the deadlock state. We have an algorithm running in the background that tries to detect it, and then we have a recovery scheme. One of the things we have to consider is how often will deadlock likely occur, and how do we handle it? Do we have to be able to roll back the activities of a process that gets killed, basically gets their process stopped? And if the detection algorithm is evoked arbitrarily, there may be many cycles in the resource graph, and so we may not be able to tell which of the many deadlock processes caused the deadlock. And so we may have a situation where we start killing off a bunch of different processes, in an effort to cure the deadlock. So different approaches is we could abort all deadlock processes and say, okay, everybody that's possibly involved in deadlock gets terminated. We can abort one process at a time until the deadlock cycle is eliminated. We just go boom, wait a little bit, still deadlocked, kill another one. Well, unfortunately not until we finally get to a situation where the deadlock cycle is eliminated. But the key question that you should have in mind is what happens when you start killing off these processes to the other processes that are doing their activities? If those processes aren't in effect, are you actually accomplishing the goals that you're setting out to do with the program? And so key things is in which order should we choose to abort? It could be based on the priority or how long has the process computed so far, and how much longer does it have to complete? Maybe involved with the resources the process has used, which resources are most likely to have caused the contention, which resources have the most number of processes that are trying to access it. And then is it even possible to detect deadlock is Ochira's question. And Ian says, and how long would it take? Does it happen immediately or it take some time? And basically what you would see is a process that is in the CPU that has access to the CPU that is not progressing. It's in some wait state where it's just hanging on and not proceeding. How quickly can it be detected would depend on what you had your monitor process doing. But the difficult part is if your monitor process can't get access to the CPU, how do you know? So yes, that is a very hard problem to solve, and that is why it's difficult. You could have a scheme where a monitor process is allowed to interrupt into it, even though nobody else is. That's given special permission to jump into the CPU. But again, you have this monitor process that's looking for deadlocks that is periodically jumping into your CPU all the time for an event that we hope and believe won't happen very often. It is a performance hit that usually is not acceptable in terms of its performance hit on the system. And then is the process interactive or batch, et cetera. So there's all kinds of conditions that need to be considered. But again, just reiterating, it is more of an academic exercise. So Ochir says, give monitor own thread would be too expensive, right? Yes, that's correct. It would be very expensive, and that is why it generally is not done. Recovery from deadlock resource preemption, selecting a victim is minimum cost. Rollback, return to some safe state, very expensive. Starvation, same process may always be picked as the victim, including number of rollbacks and cost factor. So you could have a process that is always getting killed if it ends up in a deadlock situation. So it could have a side effect of starvation of a process. So that is the whirlwind tour of deadlocks. So the main thing I would hope that you have gotten from this presentation is the fact that unfortunately at this stage of the game, and actually it's been since I took operating system, so you could only imagine that was eons ago, it has remained a academic exercise, and there has been no practical solutions to that particular issue. Only things that you can do to mitigate or to lessen the possibility of a deadlock. So moving on to the next presentation. So hopefully you see the main memory slide. So let's go ahead and dig in. Let me bring up my team viewer just so I can see my chat. I'll just get, all right. So the objectives is to provide a detailed description of various ways of organizing memory hardware, to discuss various memory management techniques, including paging and segmentation. And like I said, this is important for you to know, especially when you're trying to evaluate the performance of your application software. So even if you're not directly doing programming for an operating system, you do need to be aware of it as you're trying to optimize your code performance. So how many of you recall the time when on the Microsoft Windows software, there were two types of memory? There was the regular memory, which is the amount of memory that can be addressed with the address space that was provided by the instruction sets. And those that were so-called extended memory, where you had additional memory, but it had to be accessed in a different manner. And so therefore had a little bit extra performance hit and also involved a different way to access memory. Anyone recall such a time when there was this concept of extended memory? Yeah, that's what okay, so Scott remembers those times, yeah. Anybody else? Yeah, I remember doing a system where I needed more memory than can be done in the conventional memory. And in his intro to microcomputer design, yes, exactly. Was that with Dr. Gowing, or was that in a different instructor, Scott? Oh, different. Okay.
It was Dr. Kim.
Oh, okay, Dr. Kim. Okay, so he's in the double E department, right?
Yep, or CE or something like that. Probably double
Okay.
E.
Yeah. Right. And I believe Dr. Kim and Dr. Gowing are pairing up together to write an operating system. I mean, not operating system, to write a textbook. So you may be interested for when that possibly comes out. So yeah. So I remember writing a program in a language called Turbo Pascal, and I imagine none of you have seen Turbo Pascal, but I had memory storage needs that I had to use the extended memory, and I had to buy a third-party library to hang on to the ends of the compiler in order to access this memory. So the compiler did not even support the use of extended memory, and I had to buy a third-party tool and accessory that added hooks into the language that you would access through data ports and such to allow you to access this special extended memory. Now you generally have fairly large memory spaces as we've gone to this 64-bit computing environment. So the memory basics. So when we execute a program, or when the operating system executes a program, it must be brought in from disk into memory, and for a process and put it into the process's memory space in order for it to be run. So it has to be loaded into memory, or as we see later, at least a portion of it needs to be loaded in from memory. Main memory and registers are only storage. CPU can access directly. And we know that we have a limited set of registers that are involved with the CPU because it is more expensive than main memory. So there's only a limited. So for the most part, it is main memory where things are stored at least for longer term storage. It's things that you're accessing continuously at the moment that get stored in the registers. Memory unit only sees a stream of addresses and read requests, or addresses and data for write requests. So this is We'll discuss a little bit of the memory unit, the main memory unit, which is a piece of hardware that supports use of memory, to access to memory, since it is such a critical part of running a program. So in general, so we have that register access happens in one CPU cycle or less, and then main memory access can take many cycles, causing the situation called a memory stall. And so we saw this in our CPU scheduling, where the process scheduler can take advantage of when a process is waiting for things to be brought in from memory to allow another process to do some computing in the CPU. Again, you have to be manage this in terms of context switches. What are the performance hit with context switches, which again is involving access to memory. And then we have cache that sits between main memory and CPU registers. This is faster, more expensive memory that exists as a buffer between the CPU and registers and the main memory. And then we have the operating system has to provide protection of memory to ensure correct operation. We can't allow processes to access another process's memory in an invalid way. Basically, they have to be given the permission or allowed to access the other process memory, and they should not be able to access the other process's memory when it hasn't been agreed upon that memory will be shared between those processes. So there has to be in place a method of protecting access to memory. So the basics of accessing memory is that you generally have a base and limit registers. So the base is the first location in memory that a given process is allowed to access. So you see in this diagram, it's 300040 is the base. And then we have the limit. This is the amount of memory that the process is not allowed to access beyond. So we have the base and the limit, which then characterizes where the process is allowed to access the memory that is allowed to access. So then we have the concept of address binding, because your programs, you don't want to have to write knowing where its base and limit addresses are. You don't want to have it dependent on these and therefore have to continuously rewrite your program and changing it depending on where your base and limit address is. So, so for convenience, the process address always starts at 0. But how can that be? Because we have multiple processes in the memory, and they all can't be given location 0 as their base. And so this is the so this brings up the concept of address binding, where basically the program is given the illusion that it is addressing memory at location 0, but is actually in fact being mapped or bound to the actual physical address. So now we have this concept of a logical address, which is the view that your process sees the memory and addresses of the memory, and then the physical, which is the actual addresses that the hardware addressing it is codified in. So we have the source code address is usually symbolic. So again, even abstracting it more, there's usually some symbolic location of where the source code addresses are located. And then we compile the code to bind it to a relocatable address. So there's a base, and it's 14 bytes from the beginning of this module is an example of how it would be bound. So it could be either relative to the beginning, or you could have module definitions, and we'll look at various techniques like segmentation and things like that, modeling that tries to make it closer to the way a program actually uses it. But in the simple case, the code is compiled in a relative fashion, addressed relative to some known point, and then the linker or loader will bind the relocatable address to an absolute address so that it can be easily be relocated. Here we're talking about before runtime, so this is not actually during runtime that we're talking about. This is a linker or loader is loading it to some absolute address with the linker loader. So the binding basically maps between the logical and the physical address spacing. So here we is just sort of a diagram of the general way that a program is written and run. We have compile time, which is compilation. We have load time, which is the linker loader aspect. And then we actually have execution time, which is dynamic. So we talked about dynamically loaded libraries, DLLs, some of you may have heard of. These are dynamically done. They're done at actually runtime. So we'll look at the three phases then. Compile time is the memory location must be known apps before, and you compile it into a known location. The absolute code can be generated, and we recompile if the start location changes. And so number one is the way that MS-DOS worked. Microsoft DOS worked in exactly this way. So that's the .com format would actually be compiled for an absolute location, and then must be recompiled to start at a different location. And so you can imagine that MS-DOS was not multi-threaded, multi-process. It was pretty static in terms of having multiple processes. It was a single process situation. It was not multitask. Load time, you must generate relocate code at load time in linker loader. And so then there is a mapping that happens once we know from the compiler code, we map it once we load and know where we're going to be loaded, we then relocate the code. And then execution time, and this is where the binding is delayed until runtime. And this is how most general operating systems work in the current day. We are actually resolving it at the addresses at runtime. And in order to do this efficiently, we do rely on the fact that modern hardware provides support for address mapping, like having base and limit registers involved in the memory management unit. So I've already brought up the term logical physical addresses. This is a slide that addresses this. So the logical address is generated by the CPU, also referred to as a virtual address. And then we have the physical address, which is the address that is seen by the memory unit. So again, the logical address is the virtual reality of the CPU, but then gets mapped to actual physical addresses as seen by the memory unit. And again, we rely on hardware support to help us in this transition when we do it during execution time. Logical and physical addresses are the same in compile and load time address binding schemes, but then logical, virtual, and physical address space differ in execution time address binding scheme, and that's why we need hardware support, because we need to do this on the fly. A logical address space is a set of all logical addresses generated by a program, and the physical address space is dependent on actually how much memory you have and the physical addresses that are involved with that memory. So that takes me to my 5-minute warning. So next we're going to be covering the memory management unit. But does anyone have any question about the class or this lecture before I excuse you? So I see that most of you have got in your Chapter 4 threading program. I didn't check to see if everyone got them in, but I see that the vast majority of you got your Chapter 4 threaded programming program in. The next one will be a programming assignment on process synchronization. And in fact, if I remember right, it is actually doing the dining philosopher problems. And I haven't changed or established the due date for that programming assignment, but that is definitely something that will be coming up as the next thing to do. And probably after that, we will have the quiz on process synchronization, because I think we already had our quiz on threads. So anyway, unless there are any other questions, I will go ahead and dismiss you and look forward to seeing you on Wednesday. All right, you are dismissed, and stay online if you have any questions you'd like to ask me.